All right, so let's dive into this world of FPGAs, ASICs, and SOCs. And I know you're a digital design student listening out there, so we're going to tailor this deep dive specifically for you. It's kind of like bridging the gap between all that digital logic you've been learning and how it all comes together in these chips.
Yeah, definitely. It's a fascinating area, especially for someone with your background. We'll break down these terms, we'll show you how they relate to concepts you already know, like state machines, and hopefully get you really excited about all the possibilities out there.
Sounds good to me. So first things first, I guess, let's define these terms. What exactly are FPGAs, ASICs, and SOCs? And I guess, how do they differ?
All right, well, let's start with the most rigid of the bunch, ASICs, application-specific integrated circuits.
Okay.
And as the name suggests, they're custom-built for a very specific purpose. Good analogy is like a tailor-made suit. It's a perfect fit, but it's going to cost you more, and it can't be easily altered later on.
Oh, okay. That makes sense. So where do ASSPs fit in? Are those just kind of a less specialized version of ASICs?
You could say that, yeah. ASSPs, application-specific standard parts.
Okay.
They're like off-the-rack suits.
Okay.
More versatile, cater to a wider range of applications. Might not be as perfect as that ASIC, though.
Interesting. Now, let's talk FPGAs. I've heard they're like the Legos of the chip world. Is that accurate?
That's a pretty good analogy.
Okay.
FPGAs, or field programmable gate arrays, they're all about flexibility, reconfigurability. Unlike ASICs and ASPs, where the functionality is fixed, during manufacturing,
Right.
FPGAs can be reprogrammed.
Wow.
To implement different logic circuits after they're made.
So how do they achieve that? How do they achieve that reconfigurability?
Well, at the heart of an FPGA, you've got these things called configurable logic blocks, or CLBs.
CLBs?
These CLBs are like the individual Lego bricks.
Okay.
And each one contains these smaller elements, like lookup tables, LUTs.
Gotcha.
That can be configured to implement any Boolean function.
Ah, so that's where the connection to digital logic comes in. So all this stuff we've been learning about logic gates and Boolean algebra, that's all directly applicable to what's happening inside those CLBs.
Exactly. Each CLB can be programmed to mimic the behavior of those basic logic gates.
Wow.
Now, here's where it gets really interesting, especially for a digital design student. Remember state machines?
Yeah, we've been studying them extensively, those sequential circuits that control the flow of logic based on different states and inputs.
Precisely. And you can actually implement entire state machines directly using CLBs on an FPGA.
No way.
It's like taking those abstract state diagrams you've been drawing and bringing them to life in hardware.
Wait, seriously, how does that actually work?
Well, each CLB can store the current state of the state machine using flip-flops.
Okay.
And then those LUTs we talked about earlier, they can be configured to implement the logic. That determines the next state based on the current state and inputs.
So the CLB is essentially acting like a miniature programmable state machine controller.
You got it. And to make things even more efficient, FPGAs often have dedicated resources specifically designed to handle state machine implementations.
Wow, that is a really powerful concept.
Yeah.
This is definitely starting to click for me. I'm seeing how, the theoretical world of digital logic maps onto these physical components. Now, where do SOCs come into play?
So SOCs, or systems on a chip, they represent a higher level of integration. They combine various components, including processors, memory, and peripherals, all onto a single chip.
So it's like an entire system compressed onto a single chip.
Exactly. Think of your smartphone.
Oh, okay.
Likely powered by a sophisticated SOC, and this is where the lines kind of start to blur a little bit. You see, we now have these things called SOC-class FPGAs that incorporate hard processor cores like ARM processors right alongside the programmable logic fabric.
So it's like having the best of both worlds.
Right.
The flexibility of an FPGA and the processing power of a dedicated processor.
Exactly.
That's pretty amazing.
Yeah.
But how does that actually work in practice? I mean, if I'm designing a system, how do I decide what goes on the FPGA fabric versus what runs on the processor?
That's a great question, and it gets to the heart of what we call system-level design. You have to think about what tasks are best suited for each. For example, you might have a complex algorithm that needs to be executed very quickly. That might be a good candidate for implementing on the FPGA fabric, as custom hardware. On the other hand, tasks that require more flexibility, involve a lot of decision-making, might be better handled by the processor running software.
It's about finding the right balance between hardware and software depending on the specific application.
Exactly. And that's why understanding both digital logic design and embedded systems programming is becoming increasingly important. It's no longer just about designing circuits, it's about designing entire systems.
Yeah. Okay, I'm starting to see the bigger picture here. Now, going back to FPGAs and state machines, I'm still a bit fuzzy on how those CLBs actually handle the complexity of a real-world state machine. Can you give me a more concrete example?
Sure. Let's imagine you're designing a simple traffic light controller.
Huh?
You got your red, yellow, and green lights, and you want them to cycle through a specific sequence, based on timing, or maybe even sensor inputs from crosswalks.
Right, that makes sense. I could probably draw a state diagram for that right now.
Exactly. Now, each state in that diagram, red light, yellow light, green light, would be represented by a unique combination of bits stored in flip-flops within a CLB.
Okay.
The LUTs within that CLB would then be configured to implement the logic that determines the next state based on the current state and any inputs, like a timer reaching a certain value or a pedestrian pressing a button.
So it's like the CLB is constantly evaluating its current state, and the inputs then using that information to figure out what the next state should be.
Precisely. And it does this incredibly quickly, allowing for those state transitions to happen, smoothly and in real time.
That's pretty impressive. So you could have multiple CLBs, each representing a different part of the traffic light controller, all working together in sync.
Absolutely. You could have one CLB handling the timing, another one handling the pedestrian inputs, and so on. They'd all be interconnected through the FPGA's programmable routing fabric, allowing them to communicate and coordinate their actions.
Okay, I'm starting to see how the complexity can scale up. You can essentially build an entire system on an FPGA by breaking it down into smaller interconnected state machines, each implemented within a CLB.
You're getting it. And the beauty of this is that if you need to change the behavior of the traffic light controller, you don't need to redesign and manufacture a whole new chip. You just reprogram the FPGA, tweak the logic within those CLBs, and you're good to go.
That's a powerful capability. Now, I'm curious, what are the limitations of this approach? Are there things that FPGAs just aren't good at?
Well, there are trade-offs with any technology. While FPGAs excel in flexibility and prototyping, they might not be the best choice for high-volume production runs, where cost and power consumption are really critical factors.
So when would you choose to use an ASIC instead of an FPGA?
When you have a very specific application in mind and you need to squeeze out every ounce of performance and power efficiency, an ASIC might be the way to go. Take Bitcoin mining, for example. Requires specialized hardware that can perform very specific computations extremely quickly and efficiently. An ASIC designed specifically for that task would likely outperform a more general-purpose FPGA.
But wouldn't designing an ASIC be a much more involved and expensive process?
It definitely is. Designing an ASIC is a major undertaking, requiring specialized tools, expertise, and a significant investment of time and resources. It's not something you do for a prototype or a small production run.
So FPGAs are like the sprinters, quick, adaptable, great for experimentation, while ASICs are the marathon runners, built for endurance and specialized performance.
That's a good analogy, and that's why understanding both technologies is valuable. As a digital design student, you might start with FPGAs to prototype and test your ideas, and then if the application demands it and the volume justifies it, you could move to an ASIC implementation down the line.
This is all making a lot of sense now, but I'm starting to feel like we're just scratching the surface here. What would you say are some of the most exciting, frontiers in the world of FPGAs and these other programmable chips?
Oh, there are so many. One area that's particularly hot right now is using FPGAs for AI acceleration.
Really? How does that work? I thought AI was all about software and algorithms.
It is, but those algorithms often require massive amounts of computation, which can be very demanding on traditional processors.
Yeah.
FPGAs, with their ability to implement custom hardware tailored to specific algorithms, can significantly speed up those computations.
So you're saying you can actually build dedicated hardware circuits on an FPGA that are optimized for running AI algorithms.
Exactly, and that's just one example. FPGAs are also being used in areas like high-performance computing, image and signal processing, and even in cutting-edge fields like quantum computing.
Wow, that's incredible.
Mm-hmm.
It seems like the potential for FPGAs and SOCs is just limitless.
It really does feel that way. And for a digital design student like you, it's an exciting time to be entering the field. You have the opportunity to learn these technologies, push the boundaries, and who knows, maybe even invent something revolutionary.
I like the sound of that. This has been an eye-opening conversation. Thanks for breaking it all down for me.
Yeah.
I'm definitely feeling inspired to dive deeper into this world.
It's been my pleasure. And remember, this is just the beginning. There's a whole universe of knowledge and possibilities out there waiting to be explored.
All right, before we get too carried away with all the possibilities, let's take a moment to reflect on what we've learned and where it all might lead. We'll be back in a flash to wrap up our deep dive into this fascinating world of FPGAs, ASICs, and SOCs. We've covered a lot of ground in this deep dive: FPGAs, ASICs, SOCs, state machines, even touched on AI acceleration a little bit. I gotta say, as a digital design student, I'm really starting to see how relevant all this is, to my studies and my future career.
Oh, it's incredibly relevant.
Yeah.
And it's only going to become more so. The demand for skilled digital designers who understand these technologies is it's growing rapidly.
So if I were to walk away from this conversation with just one key takeaway, what would it be?
Focus on understanding the fundamentals.
Okay.
Don't get too caught up in the latest buzzwords or, specific chip models. What's important is to grasp the core principles of digital logic design, how circuits work, how data flows, and how to translate those concepts into actual hardware.
Because those fundamentals can be applied across different technologies, right? Whether it's an FPGA or an ASIC or even something that hasn't even been invented yet.
Exactly. The world of technology is constantly evolving, but those underlying principles, those remain constant. You build a strong foundation in those principles, you'll be well equipped to adapt to whatever new innovations come along.
That's reassuring to hear.
Yeah.
It makes me feel like what I'm learning in my classes isn't just theoretical. It's actually, going to be directly applicable to real world problems.
It absolutely is. And those real-world problems are becoming increasingly complex and interesting. Think about the challenges we're facing in areas like artificial intelligence, climate change, healthcare. Solving those problems is going to require innovative solutions, and those solutions are going to involve sophisticated hardware at their core.
So as digital designers, we have the potential to make a real impact on the world.
You do, and the tools and technologies at your disposal are more powerful than ever before. FPGAs, SOCs, advanced design software, they're all there for you to explore and experiment with.
This has been an incredible journey. We've gone from the basics of digital logic to the frontiers of AI acceleration, all in the span of a single deep dive. I'm walking away from this with a newfound appreciation for the power and the potential of these technologies.
It's been my pleasure to share this journey with you. And remember, stay curious, keep learning, and never be afraid to push the boundaries. Who knows what incredible systems you'll create?
Thank you for joining us on this deep dive into the world of FPGAs, ASICs, and SOCs. We hope you found it as enlightening and inspiring as we did. Until next time, happy designing.